In the previous sessions, we have looked at the sine, cosine, and tangent series. Now let's look at exponential series. This is not e to the power of x minus 1, it is part 1 of exponential series. Now, definition of E is limit as n goes to infinity of 1 plus 1 by n to the power of n. So starting with this, we are going to figure out what the series is. Applying the binomial theorem, we get 1 plus 1 by n to the power of n is equal to the sum k equal to 0 to n of n choose k times 1 by n to the power of k. Now expanding the general term, n choose k times 1 by n to the power of k is equal to n times n minus 1 times n minus 2 times ... times n minus k plus 1, the whole thing divided by k factorial times n to the power of k. Now here, what we are going to do next is take out this n from each of these brackets. So how many will we be taking out? We will be taking out n k minus 1 times, and one n is already there. So we end up with n to the power of k in the numerator. So n to the power of k and n to the power of k gets cancelled out, and we are left with, for every k less than or equal to n, we are left with 1 by k factorial times 1 minus 1 by n times 1 minus 2 by n times 1 minus 3 by n, and so on up to 1 minus k minus 1 by n. So each bracket in the RHS is positive and less than or equal to 1. So which means we have found the lower bound and the upper bound. So 0 is less than or equal to n choose k times 1 by n to the power of k, which is in turn less than or equal to 1 by k factorial, which implies 1 plus 1 by n to the power of n, which is equal to the sum k equal to 0 to n of n choose k times 1 by n to the power of k is less than or equal to the sum k equal to 0 to n of 1 by k factorial, and which is going to be less than or equal to the infinite series 1 by k factorial. So the sequence 1 plus 1 by n to the power of n is bounded above, since the sum, or rather the infinite series 1 by k factorial is convergent. For fixed m terms, the sum of first m terms will go to the sum k equal to 0 to m of 1 by k factorial as n goes to infinity. Cos for each fixed k, n choose k times 1 by n to the power of k goes to 1 by k factorial. Here if you notice, if we take n to infinity, 1 by n, 2 by n, 3 by n, all that disappears. What we are left is factors of 1, so which can be ignored, and we are left with 1 by k factor, which is what I have mentioned here. Now, let's write 1 plus 1 by n to the power of n as a sum of initial terms plus the sum of the remaining terms. So remaining terms summation is called tail series. So the tail satisfies the boundary. So 0 is less than or equal to the sum of initial terms, which is in turn less than or equal to the tail series. Given epsilon greater than 0, choose m so large that the summation of the tail is less than epsilon. Then for sufficiently large n, the distance between the sum k equal to 0 to m of n choose k times 1 by n to the power of k minus the sum k equal to 0 to m of 1 by k factorial is going to be less than epsilon. Since the finite part can be made arbitrarily close and the tail is less than epsilon, the entire expression differs from the infinite series by less than an arbitrary epsilon. What does that mean? It means that limit as n goes to infinity of 1 plus 1 by n to the power of n is equal to the infinite series 1 by k factorial. If we expand this right hand side, we get a series, and the left hand side, as per definition, is E. So E is equal to the summation k equal to 0 to infinity of 1 by k factorial, which is equal to 1 by 0 factorial plus 1 by 1 factorial plus 1 by 2 factorial and so on. By 0 factorial. 0 factorial is nothing but 1. So 1 by 1 is 1. 1 by 1 factorial is 1. So the series is 1 plus 1 plus 1 by 2 factorial plus 1 by 3 factorial and so on. Now this was the series expansion for E. But what we are interested in is e to the power of x. So the exponential series 1 by n factorial is convergent and its sum is denoted by e. That is what is our conclusion based on this derivation. Now, if e to the power of x is defined as limit as n goes to infinity of 1 plus x by n to the power of n, then for every real number x, e to the power of x is equal to the series x to the power of n by n factorial. And we can derive this by repeating the binomial limit argument with x in place of 1 in 1 by n. So the series expansion for e to the power of x is x to the power of 0 by 0 factorial plus x to the power of 1 by 1 factorial plus x square by 2 factorial and so on, which can be simplified to 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. That was exponential series e to the power of x. Now, if you found this session helpful, please do like, share and subscribe. Questions, suggestions are always welcome. Thanks for watching. See you in the next session. That's it for now. Bye.